Our first speaker is Carola Schönlieb. And okay, let me tell you a little bit about her bio. She was, I think, she did her undergraduate in Austria, but then she got her PhD in Cambridge. After some postdoc in Göttingen, she has been a professor at Cambridge, where she's the head of the Cambridge Image Analysis Group. And here you can start seeing what his talk is going to, her talk is going to be about. Anyway, let me tell you about all her all her achievements. And for instance, if you look at her scholar profile, she has there are more than 400 entries with almost like 10,000 citations, and this is quite impressive. And let me just make the contrast. If you go on her MathSciNet profile, there are only 90 papers and not that many citations. So you see that this huge gap is due because she's really doing applied mathematics. This is how you detect someone doing real applied mathematics, not just selling it. And okay, she has a lot of well, she's won some bunch of prizes like the Wolfson Fellowship, the Calderon Prize, the Philip Leverhulme Prize, the Whitehead Prize, and the Mary Bradburn Award. And maybe more recently, she got the prestigious EPSRC grant from the UK, that is more or less the equivalent of an European ERC grant. So I guess this is the most prestigious thing you can get in UK. And she has really created a group in her research. So like say she works on PD, calculus of variations, inverse problems, optimization. That's more from the theoretical side, but moving towards the applied side. She works on machine learning, so the theoretical foundations of machine learning, image processing, but with a big emphasis also on applications that range from fields like medicine, art, and many others. So I think it's quite impressive, all this wide array of research that you have put, Carola, and I think it's a good inspiration for all of us. Okay, maybe I should just finish concluding the title of her talk, which is it's mathematical imaging from geometric PDEs and variational modeling to deep learning for images. So I think this is quite a good summary of all her career and all research and all this impressive work. So please, Carola, feel free to share your screen and start when you are ready.
Thank you so much. Thanks for the really beautiful introduction. It's I think you've hit the nerve of the kind of work I do and I love to do very, very well. So thank you so much. And thank you, Michaela, and the whole Women in Math committee for inviting me to give this presentation. So let's hope this works now. Can you see the full screen, the slides? Okay, perfect. And actually going back actually to something that you mentioned, that the work that I do on the mathematical side spans quite a wide range of different mathematical areas and concepts, is really due to the fact that mathematical imaging is just extremely rich in general in terms of these mathematical areas appearing. And I hope I'll give you a sense of that in this presentation, which actually, as Maria said, is really meant as almost like a whistle-stop tour through different things that appear in mathematical imaging, both on the mathematical side, but also on the applications side. So what are the kind of things that we get excited about? What are recent trends, research trends, and what are, on the applied side, the problems that we deal with on a daily basis? Okay, so I want to use this talk really to answer the question, what is mathematical imaging? And I would like to do this in a multi-scale fashion, kind of. So starting with a macro definition, and then going a bit more into detail by showing you both examples of the mathematical problems that appear and of the application. So starting with the definition, yeah. And by the way, this is a definition that I came up with. So maybe if you ask different people, this will vary slightly. But for me, mathematical imaging is the study and development of mathematical methods for image analysis, image processing, and inverse problems in imaging. And I would say what makes these methods, these image analysis processing methods, very different to what I would maybe engineers or computer scientists are developing, is that we are really interested in understanding how these methods work, when they fail, and what kind of solutions they are able they're able to produce. Yeah? Right. So now I'm going more into detail to explain a little bit more what is behind this definition. And I want to do this in these 4 parts, basically, of this presentation. First, I want to go through problems that we want to solve. And this is a kind of a categorization of the kind of things that appear on a more abstract abstract level that we want to solve and we want to develop mathematical methods for. Second part is going into the application. So where do these problems actually appear? In which situations? In which disciplines? How do we solve these problems? So this is talking about mathematical approaches. And again, because this field is so extremely broad and diverse, I'm going to cherry pick a few concepts that at least influenced the research that I'm doing quite a lot. And then I'll go into recent trends and what I call challenges. So what is it that mathematical imaging people are currently excited about, and what is it that they are worrying about and developing solutions for. Okay, so first of all, the problems we want to solve, and this is already a good example of one of those, which is image denoising. But again, starting on a macro level, so the common goal in mathematical imaging is to extract information from large, diverse, and corrupted imaging data in an automated and robust way. And so this information could come in various forms. It could come in the form of an image, like in this image denoising example. Yeah, so you start with your imaging data, which is a noisy version of the image you're actually interested in. And the task here is to remove the noise and get something that is, well, guaranteed to be, under certain assumptions, to be guaranteed to the actual clean image that, of course, in practical applications, you usually don't know. It could also come as some type of quantification of the imaging data. This is an example of something that is called motion estimation problem, where you're starting with a video. So this is just one frame in this video, and you want to quantify in some way. You want to visualize and then also quantify how motion in this video happens. Yeah, and this you can mathematically describe by a velocity field, by a vector field, which where the direction of your vector in every point tells you in which direction you're moving. And then the length of this vector tells you how fast you're moving there. And this is a visualization where this is color coded. Yeah, so the color coding here tells you the direction. So if you look at the frame here, you can see that blue things are kind of moving more in this direction, red things are moving in this direction, and then the saturation of the color tells you the speed. Yeah? So this is one example. Another one is where what you get out is an image, where you starting with a very, very low resolution image, and what you want is by adding some prior information, which in this case is a high-res image from another imaging modality. You want to create a high-resolution version of this image, or that happens a lot in imaging in general. This could also be a segmentation, yeah. So where you're interested in delineating, detecting certain objects in images, well, for several reasons, right? Depends on your application. And so in general, here is a categorization of the different things that at least encapsulates a lot of the things that we are dealing with. So image denoising, I've already touched upon. You can mathematically phrase this as you're measuring some data that is your clean image plus, and this is when you have additive noise, for instance, you model it as an additive random component. So N could be, for instance, white Gaussian noise. So based on Y, on a noisy version of the clean image, you want to compute U. You want to compute something that I call here U star, that is close to the clean U. That, of course, you don't know. Segmentation, we've seen already. Mathematically, you can phrase this by saying, given an image U that is supported on some domain omega, that is usually a rectangular domain in image processing, you want to compute, well, you can phrase it as the support of the objects that you're interested in, and here you could phrase this as the characteristic function of a subset of your domain, where this subset, by the way, it doesn't need to be connected, right? So this is why this could be several cells here in this image that you want to detect. Image reconstruction, very closely related to image denoising, is another very, very important topic that in particular appears when you are dealing with scientific and medical imaging, where often the machines that people use to visualize things do not produce an image directly, but they produce some transform of this image, and usually it's not a clean transform and it's not a complete transform, but you have noise in the data and you have undersampling, so you have missingness in the data. And based on this noisy, incomplete data, you want to reconstruct the underlying image that then, of course, people in applications can use to do things further. And then last but not least, I've also picked image classification to pick out, which is also in a way related to segmentation if you want, but here the idea is that you either have an image and you want to classify each pixel in this image towards a different class. In this case, this is a satellite image, and you want to classify each pixel into a different type of land cover. Yeah, so this could be for could be, you want to understand what is here, where is rice or barley or something like this. Yeah? And you can do this from imaging from a particular type of imaging data, which is called spectral imaging data, which gives you also material properties of what you're imaging. Yeah? So here RGB images will not be enough, by the way. So this is one type of image classification, or as I've written it here, actually, you could also think that you have a data set of different images and you want to classify these images into different classes. Yeah, so you want to assign labels to the images in your data set. Yeah, so like cats and dogs or something like that. All right, so these are the kinds of problems we want to solve. And why do we want to solve them? Well, some of this has been already revealed here, because all of these type of images come already from applications. But let me give you a few more examples. So the first one here on the intro slide actually is, again, an example that is very close to my heart, because it was the first interdisciplinary collaborations I had when I moved to Cambridge, which was with a zoologist. The idea here is the zoologist has been doing research on this kind of bird, which is called pied flycatcher bird. And these are migrating birds. They come to Cambridge for breeding. And so somewhere a little bit outside of Cambridge, they have these nesting boxes. And so they come there. And the hypothesis this postdoc at the time, Hannah Rowland, had was that the size of this white blaze on the forehead of the male pied flycatcher bird is correlated with their reproductiveness. So meaning basically that they are more attractive for the female species than so the ones with the larger blaze basically are more attractive than the ones with the smaller blaze. I will not make a joke about this now, but the thing is that what she did in order to try to prove this hypothesis is that she went to these nesting boxes, and she basically caught, as you see here, she caught these birds, held them in one of her hand, took a ruler. She did this all by herself, by the way, took a ruler and then took photographs. And she wanted some quantitative way from these photographs to measure the size of the blaze, and so that's what we did. We helped her with, and you can see what is involved in this little small video sequence. But again, going to through applications a little bit more categorical by application area. The first area I want to mention, which is also the one that we mostly work in, is biomedical research and clinical support. So there are a lot of problems where automated interpretation, automated getting the most out of measured imaging data in terms of image quality appears a lot. And so here are just a few examples of, and this is very anecdotal, by the way. I'm just showing you things of the kind of things that we are doing, because it's very easy for me to talk about them. And I like them, of course. So the first two examples are examples of problems where you are measuring some data with some imaging machine. The first one here is positron emission tomography. Unfortunately, I don't have time to go into the specifics of how all of these things work. But again, they don't measure an image directly. And the other one is spatiotemporal magnetic resonance imaging. And in both cases, we are dealing with the problem of having noisy undersampled, so incomplete measurements. We want to make the most out of this data, so get the best images back. And this has different implications for different use cases. Here in the first use case, it really is about increasing the spatial resolution so that the clinicians can see and quantify better things that are going on in our brain. So on a very high level. And in the second image, it's really about the trade-off or balancing the temporal and the spatial resolution in a way that you see enough spatial details, but also on a fine temporal scale, which means the kind of mathematical models that we develop are both making the spatial resolution better, but also the temporal resolution. And that's important, if in particular, if you're interested in dynamics, but also it's important when you want in a clinical setting, when scanning time is actually of the essence of not making people lie in a magnetic resonance scanner for too long. Yeah? The next examples are more quantification examples. So the one we've already seen, estimating dynamics, this was a collaboration with some people in biology who were interested in embryos, so in so-called oocytes of flies, so Drosophila oocytes and early development, basically. This was with people in cancer research where they were interested in mitotic cells, and in particular understanding mitotic cells under the influence of chemotherapy, so under the influence of drugs that should inhibit mitosis. And what we basically did is just made the life of them easier, not to go through these frame by frame, but actually helping them to detect and also track these mitotic cells and determine their fate in the end. Yeah? Tumor segmentation or segmentation in general is a big topic and appears in all kinds of settings. And again, is something that can make the life of, in this case, radiologists so much more interesting and easier, because it's a very tedious and very non-interesting, not very intellectual work to actually do this all by hand. In particular, because these are usually not just 2D images like you see here, but these are 3D volumes, right? So many slices you need to go through here. And the other one that I think is also super interesting, and you hear also a lot of talk about recently, in particular with deep learning approaches appearing, that can actually capture some intrinsic information in large data sets, is the application to diagnosis and prognosis in the clinic. So to aiding diagnosis and prognosis based on, you have a large data set of something, right? For instance, of people with a certain pathology or with a certain history, with a certain clinical history. And you want to learn from this data set and make and help patients in the future to make better predictions when they come in with certain symptoms. Yeah? Okay. Another big one that we've been also working on a lot is in the context of conservation and sustainability, which on a more abstract level maybe is a subset of what people call remote sensing. So you sense objects from far away. Either you sense them like here from the sky, so from airplanes, or from airplanes, or from space, right? Satellite imaging data. Or you sense things like when driving with your little Google camera or something like this on top, and you sense things down on Earth. Working with remote sensing data mostly means that you want to again quantify information automatically from these images. Becomes more and more important nowadays, with more and more remote sensing data being collected, and really huge opportunities to understand what is going on with our world on various levels. We're interested more on the conservation side and the sustainability side. But this, of course, has also huge implications for things like agriculture and all of this type of stuff. Yeah, I think actually looking at these videos, you probably already got a sense, so maybe I'll just continue. Another big area of applications for us, which is maybe coming in as a little bit of an outlier compared to the others, is digital humanities. So here, again, this is, I think, is an area that is highly under researched in terms of you know, people in image processing, image analysis actually working on these type of problems. But it's extremely rich, yeah, because more and more in museums is digitized, and there are more and more opportunities to play around with this imaging data. And maybe also to help the museums to curate and to sort through, detect patterns in data sets that they haven't seen before, and make new connections, new interesting connections. And actually, again, here on the digital humanities side, the data that is being collected usually is also often nowadays not just images, so not just RGB images, so normal photographs, but often is actually even also, again, more interesting. So spectral imaging, as I explained briefly before, is another thing that is being collected a lot. There even tomography is being used that we usually just encounter in the medical domain. Yeah, and here you just see a few examples of what is called image inpainting or image restoration, where the task, I haven't explained this yet, but where the task is you have an image, you have part of this image that is being damaged, like in this case, so what is highlighted here in yellow are scratches, and you want to remove the scratches and replace them by something that that is suggested by the intact part of the image, and so so this is a kind of interpolation problem, right? You can phrase it as an interpolation problem. And so one reason why I actually, you know, got into imaging myself was via image inpainting, via image restoration. Because at the time when I did my PhD, the kind of state of the art for image restoration were actually using partial differential equations to solve this restoration task. Yeah, yeah, we'll get to this in a moment. Yeah, and then there are many more application areas. So these were maybe 3 main ones, but there's a lot of imaging happening, of course, in material sciences. I'm mentioning molecular biology next because actually what you see here is slightly connected, because both of this is using electron tomography or electron microscopy to look at things here. The things that people are interested in are so super small on a nano level, right? That actually you use very highly sophisticated tomographic machines to look at things. Computational fluid dynamics is also something that we did a lot here in Cambridge, because there is a very strong group in chemical engineering who are using magnetic resonance tomography to look at fluid gas flow. And the zoology I've already mentioned. Okay, so now we've looked at the kind of things we want to solve. We have looked at why we might want to solve them. Again, I hope you got you got a sense for the fact that on an application level, so if you want to work as an applied mathematician, meaning that you want to do some interdisciplinary work, I think imaging is a great field, because you can pick and choose in which application areas you want to work, since images appear almost everywhere. Yeah, in almost all disciplines, images appear in some shape or form, and people use images to either feed into their research or feed into real world settings, like in the hospital or something like this. Yeah? So I think that's what was one of the things why I was quite excited about mathematical imaging. Right. So now mathematical approaches, and I think I'll jump over this 4 V's, because I'll just want to go there. So before thinking about how to solve all these things, right? Or when you start thinking about how to develop solutions for these different types of problems that I told you about, there are a few additional things that might be good to keep in mind when attempting, for the first time to develop these methods. And really the main thing is here in this box is to realize you will not get nicely clean, curated, perfect imaging data. Yeah? So usually the type of data that you get, in particular, if you work with real data, yeah, and I'm emphasizing this because again, and I think so. I think Ma Gonzalez, you have actually said it already before with this thing about where my citations are. A lot. There are many people, or you know, there are also in mathematical imaging or computer vision people who do lots of methods development. But always stay in the kind of nice, clean benchmarking data set world where you develop methods and you basically try to try them on standard curated data sets. I think a lot of problems really only appear and only become visible if you work with real data. And that is in particular how messy it is. And the other thing that we really need to keep in mind, which is I think why mathematicians is really important that mathematicians work on this, is that often what we are measuring with our imaging device is used to look at things that we otherwise cannot look at, either in medical imaging because we don't want to cut someone open to be sure whether they have cancer or not, but we want to use imaging first as a first indicator, or because, like the examples I've shown you with material sciences or molecular dynamics, because things are so small that we can't see things with the naked eye. So we need imaging to look at this, and in particular in a research context, we often don't know what is going on. We look at new things, at new materials, at new proteins that we want to understand, yeah, and we want to use imaging to understand things. So hence, why is this a link to mathematicians? Because the methods that we are developing and apply to be able to do this do come with mathematical guarantees. Yeah? So they come with guarantees in the sense that, well, solutions actually exist to this problem, right? That to this approach that we are proposing. They make the problem is on even on a in a more general sense is well posed, and it's where the well posedness also in this setting, it's not just how the solution exists, but the solution is actually also going to be meaningful, even if I have noise in the data. Yeah, so which comes with the continuous dependence on the data you are starting with. So the requirements are: we need to be robust to data corruption. We can handle unseen data, and that again is something maybe also to keep in mind when thinking about. Again, Ma Gonzalez mentioned machine learning as some recent mathematical approaches that are being used. This has a huge effect on the kind of things that we can use there. So we can't develop foundational models for imaging usually, because there is not so much data for medical or scientific imaging. Of course, if you go to photographs, there is a lot, and people have done things. But in particular, if you look at the more scientific medical imaging domains, this is not the case, and even if it would be the case, there are lots of things that happen that might have not been measured before. We need methods to be sufficiently accurate, and again, this should come with some underlying guarantees. It's not enough to do just a few experiments and say, yeah, this works, so it will work in the future. We really need the guarantee that it works, because lots of these applications are either sensitive, decision sensitive, like in the medical domain, or if they inform another scientific domain and people are writing research papers about new materials having these and these properties, again, you want to be sure that this is actually correct. And then the last thing, which is again quite important, is that they're computationally affordable and in particular scalable. Imaging data is usually huge. And so this means we need methods that can actually scale with this large size of the data. So what are the different methods that people have developed with all of this in mind? Yeah. And there are roughly two paradigms that people have been following. I would say the left one is the more traditional mathematical one that 99% of people in mathematical imaging have been working on before deep learning came around. So what I've called the knowledge-driven paradigm, or developing mathematical image processing methods based on first principles, which means that you look at, you start working on an application. You first try to understand the data, the physics behind how the data has been collected. You mathematically formalize this. Then you're trying to understand the type of solutions that people want to compute, right? You try to understand what kind of maybe regularity properties these solutions should have, and again you try to mathematically formalize this. And this process can then result in different mathematical models. Geometric PDEs were in the title of the talk, and this is because geometric PDEs have been used a lot in image processing, just because of the fact that geometric structures in images are usually extremely important to characterize what is going on in this imaging data. In particular, think of the fact that if you look at a CT scan and you want to detect a tumor and maybe also understand how large the tumor is, what's the shape, and so on and so forth, how the tumor sets itself apart from the rest of the tissue that is surrounding it is by some kind of edge, some kind of boundary that is around it, right? And so this is already a geometric feature that nonlinear diffusion equations like this one, this is the total variation flow in a kind of very formal way written, can model. Linked to this also variational models. Lots of the PDEs that people have been looking at are coming actually from variational models. So our gradient flows of these variational models. And I've mentioned here also multi-resolution sparsity, because a lot of the models that are being around in this more knowledge-driven paradigm come or are inspired, are driven by the assumption that images, the solution, or images, or the solution, let's say images, which are often the solution to the problems I've shown you, images are sparsely represented in some kind of representation, in some kind of basis or dictionary. Here, for instance, with the total variation flow, you say the image is sparse in the gradient representation, meaning that most of the information is contained in the edges, and everything that is in between I can nicely diffuse away and still get something that is fit to be used in an application where, for instance, I'm mostly interested of delineating a tumor. No? So this is the more principled kind of knowledge-driven paradigm. And then the more data-driven paradigm says, well, actually, I have no idea, or I don't want to think about it. So either I have no idea, or I just I just don't want to get too much into understanding what this is all about. But I have a really large data set of examples of the kind of data that I'm measuring, and also of the kind of solutions that I want to compute. And then I'm starting with a fairly general model, yeah. So, like for instance, a highly overparameterized neural network, and this is really the main thing that is happening now in data-driven imaging is neural networks, so deep neural networks as models for solving a lot of these tasks that I've shown you. And then I train this very general network on the data set, on this training data set that I have, and I create an instance of this neural network that can solve my task. Okay. So let me, I'll just try to think how I should be structuring the rest, because my plan now is to briefly talk you through each of these paradigms. But I think what is maybe better, because we don't have huge amounts of time left, to tell you. So I think, because I think I gave you some idea of the kind of mathematical mathematical objects that are appearing in particular the knowledge-driven paradigm and the data-driven paradigm. Of course, these are neural networks. So maybe I'll do this very brief and then tell you, where the exciting things appear, which are really at the interface between the two things here, between mathematical models and so the more principled models and the data-driven models. So the knowledge-driven paradigm has many forms and connotations. The main one that I want you to keep in mind is the variational approach, which, as I said, is very tightly linked to PDEs and a lot of research also, as Mar Gonzalez said, in variational calculus, geometric measure theory, and also numerical analysis of differential equations, optimization, mathematical optimization, and so on. So the variational approach says the following. And this is in particular, I showcased this now for image denoising. Yeah? So one of the first image processing tasks that we started this presentation with. So the data is given as the clean image plus some random noise component. Yeah? And here, by the way, I mean, I'm saying this here later on this slide. You can think of the objects U, Y, and N just as some elements in some generic, mostly Banach space. Actually, is the setting that we are in. And by the way, it's maybe also good to know, because in particular, I am looking at this with an applied analysis viewpoint. All the models that we derive and all the analysis that we do for these models usually happens in infinite dimensional spaces. Yeah? And of course, when we then, solve them computationally, we discretize, and this is where also research and numerical analysis comes in. But really understanding these models and what is happening with solutions of these models and so on is usually all done in infinite dimensions. Right. So hence, think of this now at the moment in infinite dimensions. So we want to solve this problem. And one way to phrase this is with a variational regularization approach. So you want to compute an approximation U of the unknown clean image as a minimizer of an energy functional that usually encapsulates two parts. One is the so-called data discrepancy or data fidelity term, that says the minimizer to this energy functional should, let's say, as a choice, this is a least squares fit, so the L2 norm squared. The minimizer should be close to the noisy image, yeah? In an L2 squared sense. But then, because if I would just solve this, I would just get y back, right? So well, if y is also in L2, let's assume that, then I want to add another term here that basically helps to denoise the image. That is the smoothing term that helps to attenuate the noise in the image, but still tries to preserve the structures, the underlying intrinsic structures in the image that is not noise, right? So this is my regularization term, is another penalty, and then these are balanced against each other with a parameter, with a usually just scalar positive parameter that tells me how much do I need to regularize and how much should I stick to the given noisy image. And this, of course, as you might guess, depends on the noise level. Okay, so the higher the noise level, the larger alpha should be, the smaller the noise level, the smaller alpha should be. And that can be made more precise. There are parameter choice rules for alpha, like the discrepancy principle, for instance, and things like this that are mathematically justified. And so one very important regularization term that links to what I said about variational calculus and this nonlinear diffusion equation that we have seen before and so on is the total variation regularization, which in infinite dimension is really the total variation measure of the distributional derivative of the solution. And the nice thing about this is, let me just go here a little bit further. Let me go here. The nice thing about the total variation is, let me see if I only have this, is that in 1D it's very easy to explain. The total variation is basically just quantifying the accumulated oscillations that you have along your 1D signal. In 1D, it's really just the sum of all of those. So the more you're penalizing the total variation, the more you will first of all attenuate these oscillations. So when you compute the solutions to your variational model, you rather want to have signals like this than signals that have oscillations. This will be immediately penalized. On the other hand, which actually I should really replace this example, because it doesn't show the second thing, it actually preserves edges in the image, and edges are really discontinuities discontinuities in your image function, yeah, where you jump from one intensity value to the other one. And this can be seen here. So here I'm running the total variation flow, starting with a noisy image. I'm sending this through this total variation flow now for an exaggerated regularization parameter. So usually you wouldn't choose the regularization parameter that large, right? Because here I'm definitely over regularizing, but just to show you the kind of effect this total variation regularization has, is exactly to preserve the edges here and to attenuate the noise. And this is, by the way, just going back here, very different to if you would just use something like an H1 semi-norm squared, which is really giving you how you call this, so where the diffusion doesn't depend on the image function itself, right? So it diffuses everywhere in the same way, and hence it diffuses as a linear diffusion process, diffuses also the edges in the image. It eventually will also completely erase the noise, but it at the same time will also smooth out the structures like edges you want to preserve. Okay, and there is again a lot of exciting mathematics that people have thought about when looking at variational models like this one. Yeah, which is both on the analysis side and also on the numerical side. And for those who are doing numerical analysis and also applied analysis, you know that they're often going hand in hand, right? So problems that appear in infinite dimensions will also reappear when you're discretizing the equation or the variational model. Yeah? So without going into detail, because the total variation brings solutions into a space, into the space of bounded variation functions that is not reflexive. There are lots of things that need to be done just for this. It doesn't come from standard theory, which even starts already with the well-posedness. But it also has very nice links to, as I said, geometric measure theory, because you can also think of the total variation and applying that to an image as applying it to the level lines of this image. So you're applying the total variation to sets rather than the intensity function. So there are also lots of nice interpretations in this direction. And then on the numerical side, a lot of the work that has been done treats the fact that we are solving a non-smooth optimization problem, and we are solving an optimization problem that's usually very large in terms, again, of the size of the data. Let me jump this. Just the total variation is, of course, not the only thing. Lots of different types of regularizer smoothing approaches have been introduced in the literature. And as you can imagine, the type of result that you get hugely, crucially depends on what you are using as a regularization, as your prior information that you're putting about the type of solutions you want to compute. I would have loved to show you this video, but I'm running out of time. Let me therefore go to the second part, to the neural network part. Yeah, so just to counter, to kind of show you how these two compare with each other. Yeah? So I think every one of you knows nowadays how neural networks, what they are and how they roughly work, right? So I think I can skip this slide. It's really an optimization. If you train neural networks, it's an optimization problem with a lot of parameters, usually given by linear terms in a multi-layer object. And in the end, once you have trained a neural network and you apply it, it's an application of a sequence of linear operations and pointwise nonlinearities to compute your solution. And so this is one example of how what deep learning can do, and this is already a couple of years old. So the kind of things that can be done nowadays. I'm sure people have seen many impressive examples of what can be done. But I'm always showing this because I've worked myself a lot on image restoration and image painting with partial differential equations. And for those of you who are working on partial differential equations or who have seen some things on, for partial differential equations before, might appreciate if you see the result of this this in-painting approach, which is using a deep neural network. It is, I think, quite tough to think about a PDE that could do something similar. Would need to be a very non-local type of PDE that, yeah. So, and this maybe shows you already the conceptual difference between the two on one level, which is that while in our first principled way, let's say with partial differential equations, we're usually very good in coming up with models that are very generalizable because they focus on the main things in the image, like edges, right? Which is not just true here for this Einstein photograph, but is going to be true for for images that are photographs, for images that are coming from CT scanners, for images that coming from microscopes. The modeling capacity is limited by the complexity of the model that we accept in terms of computational complexity, but also in terms of being able to still mathematically say something about the type of solutions that we are computing. Neural networks take this from a completely different perspective, right? They say, I really am after a solution that can really capture the intrinsic properties in images as given by a data set that I've trained them on. And if this doesn't generalize to CT images, actually, I don't care because I just train a new neural network model. If I don't completely understand how this solution has been produced, I don't care. This is just inpainting. This is just, you know, playing around with this Einstein photograph. They explain a bit, so, but where people care about both explaining this, how you get to a solution, but also so being able to explain how the solution has been computed and whether and the kind of properties the solution has, but also being able to derive models, let's say inpainting models that can work with small amounts of data is important. Yeah. And here, and I think I'm going to actually finish on that. I just want to go back to the application that I've shown you here for cultural heritage, because we are talking about inpainting here. So if I want to, so if I'm talking with art historians and they give me, in this case, these are images from illuminated manuscripts, yeah, so from a particular artist that has been painting these small illuminations. So these, for those of you who don't know what illuminations are, they are usually these kind of small drawings that are being made within manuscripts to illustrate things. Usually people think of illuminations also with these small gold particles and so on that are being used. So if an art historian wants me to come up with a plausible solution to this restoration problem, they wouldn't be happy with an inpainting approach that has been trained on lots of photographs of cats and dogs. Yeah? And maybe this is intuitively clear, right? Because the data set that these neural networks are trained on encapsulates the prior information you're using to now inpaint this manuscript, right? So either you come up with a mathematical way, like a PDE that explains how things are being done, yeah? And by the way, these PDEs often have been, the first of these PDEs have been actually modeled following how museum artists are doing a restoration process, yeah? So like continuing level lines across the missing domain in the direction of the gradient and things like this. Either this, or they might say, okay, you can do a machine learning approach, but you can only train it on images of the same artist. And so this shows you that we either you give them something explainable, or you give them something that is plausible in terms of the data set that is being used, which is usually very small. And now I'm going to finish with my last slide, which is really where the exciting things are happening, is where the mathematical PDE approaches, variational models, are coming together with more data-driven paradigms. And one example of something like this is to combine data-driven paradigms with mathematical models that are more traditional and which have a mathematical foundations like variational models. So you stick with variational models, but you play around and you make data-driven the terms that you think could profit from being more data-driven, which is this regularization term, right? It makes sense. As I said, the type of regularization used will determine a lot the type of solution I get and the quality, how well representative it is of the type of structures that I can expect in the solution. So there are different ways, and of course, if you do this combination, it's not just plugging in a neural network into this regularization term, but you need to think about how to train this regularization term. You need to think about how to train it to still preserve mathematical properties of your variational model. You might want to think how to make this also explainable. Maybe you don't want to completely over-parameterize it, but maybe you want to make it more sparse in the terms of features that it's using, so you can actually explain still, even if it's a neural network, and what it is doing and so on. So on that note, I'll finish. And I want to thank everyone for coming to this online session. It's really an honor to speak on this occasion. I thank you all very, very much. And I thank, of course, my research group for everything they've been doing in all the examples that I've shown you.